As you know, today is Wednesday, so it's a, what would I say, it's a day before Thanksgiving. So we're not going to do too much new stuff, but we'll try to review what we have done in the exam. How do you find the exam? Was it reasonable? Was it fair? Was it, did you see anything in the exam that was not covered in the lectures? They were okay. Uh, Well, some of you have done really well. You know, you scored 100 out of 100, but there are some others who have been struggling a little bit. So today we'll try to uh, go over the exam a little bit and then try to review the material, because this will be important for your finals too, because finals is going to be cumulative. So some of the topics that we covered in that lecture will also be there in the finals. The other thing is today I also uploaded a lecture on acid bases. Did you all get that one? Did you see that in the Canvas? Acid base chemistry. So that's what we'll discuss next week. We don't have too much time. So what I would like to do is, whatever time we have, we will do three important topics. One is about acids and bases. And the next one, I would like to deal a little bit about medicinal inorganic chemistry. So a presentation will be given to you sometime during the Thanksgiving. And finally, we will talk a little bit about hydrogen. You may be thinking that, well, what is there to learn about hydrogen? So we'll try to see some phenomenal properties of hydrogen. Perhaps you may not have heard about it, and why is it very important, okay, from an organic chemistry perspective. So those are the three topics that needs to be done. For the exam, what do you think the most toughest question was? Most difficult one to answer? Any comments on that? As you know, this is a descriptive chemistry, so there are not too many numerical problems in here. It's mostly about concepts and trying to understand how things work, right? Uh, so let me go over some of the questions that some people got wrong. So I made some analysis to see where people were going wrong. So let me go over those concepts one more time. Uh, I gave an example of K3COCN6. I asked you to name the complex, right? Uh, Approximately, from my statistics, 25% of the people got it wrong. To me, that is very surprising because we went over the rules, right? So the way we name these complexes is name the cation first, name the anion. Anion is the complex here. So some people try to put tripotassium. No, that is not correct. Or just simply say cobalt 3. Because this is an anionic complex, it has to be cobaltate 3. So those are some of the finer things people are missing. So this should be properly named as potassium hexacyano cobaltate 3. So that should be the correct name of this complex. So those of you who got it wrong, please correct it again in your notes. The next question that we had was on writing the formula of sodium tetracyanoaurate. So sodium tetracyanoaurate 3. That's the question in the exam. Only 10% of the people got it wrong, but remaining 90% of them got it right. So basically, you'll have tetracyanoaurate, so AuCN4, right? And you have gold in 3+ oxidation state. Cyanide has a -1, so 4 negatives under 3 makes it 1 negative. So which means that you need to have only one sodium as a counter ion. So the answer for that is going to be NaAuCN4. So those of you who got this question wrong, please make a correction there. Similarly, there are a couple of questions on the types of isomerism, which many of you have done really well. For example, when I gave CONH3 5 times Cl SO4 and CONH3 5 SO4 Cl. And I asked, how are these two complexes related? In fact, this question comes directly from the lecture notes. We talked about the very simple, very same example. So those of you who followed the lectures had no problem in answering. So I see only 5% of them got it wrong, which is not too bad. So basically, this is an ionization isomerism, because when you dissolve these salts or the complexes in water, the way they break down is very different. In the first case, you will see free sulfate anions, and in the second case, you see free chloride ions in the solution. So that's the difference. So it's an ionization isomerism. Similarly, you can always stop me anytime if you think that I'm going fast. Okay. Some of it I cannot see, but this is very important to keep ourselves reminded about these things, because we'll have a final coming up in a few weeks. The next one we had was Fe NC6 3 minus and FeCN6 3 minus. And I asked them what type of isomers these are. It's basically, in one case, it's a nitrogen that is bonding to iron. In this case, it's a carbon that is bonding to iron. So the way it links, the ligands link with the metal is different. So this is typically known as the linkage isomerism. Okay. So we talked about this too. And then I gave you a few complexes and said, which of these can never exhibit optical isomerism? For example, if I have PtCl4 2 minus. So when you look at the square planar complex, PtCl4 2 minus, as you can see, square planar complexes can never exhibit optical isomerism because at least they have one plane of symmetry. So if they have a plane of symmetry, that can never exhibit. Similarly, there is another one that I gave, which is AgNH3 twice Cl. These two complexes can never exhibit optical isomerism because one is a linear one, is highly symmetric. In general, symmetric objects do not exhibit optical isomerism. So of the choices, these two are correct. 30% of the people got it wrong here in this question. Okay, I just want to remind people. So this is something that you have to keep in mind. All right. The next question we had was, I gave you this molecule IF2 minus and asked, what is the highest full rotational axis symmetry this species has? Again, I have a 60% accuracy and 40% of the people got it wrong here. People who got it wrong perhaps is because they are not doing the Lewis structure of this molecule properly. So the correct Lewis structure of this is going to be I and F. The F will have octet and I will have 3 non-bonded pairs. So if you look at the steric number here, we have a steric number of 5. So this should be a trigonal bipyramidal geometry electronics wise. And we also talked in the class that the lone pairs always occupy the equatorial sides and the axial sides are occupied by the fluorines. So if you now look at the shape of this molecule, this looks like a linear molecule, IF. So linear molecules, we know, have highest full rotational axis symmetry of infinity. So the answer for that question is the highest full rotational axis symmetry for this is C infinity. I don't know why some people wrote it as C2, because they're forgetting this is almost like carbon dioxide here, linear molecule. So make that correction so we don't make that mistake again in the future. Then I gave you a bunch of molecules and asked you which one of them will have a C3V symmetry point group. Okay. The only example there is going to be NH3. We went over this. NH3 molecule has the C3V symmetry because it is a 3-fold rotational axis of symmetry and 3 vertical planes, no horizontal plane of symmetry. So this is the correct example, the correct answer for that question. And then I gave you some molecules and I asked you which one of them will have C infinity axis of rotation. So the examples I gave you there was HCN, CO2, NH2Cl, and perhaps NH3. So these are the 4 examples, and ask you to pick up the molecules that have C infinity axis of rotation. So clearly the linear molecules are the ones that have C infinity rotation. So that should be the correct answer from that question. And then the next question, I have given you 5 molecules and asked you which one of the molecules will have a sigma H, or in other words, the horizontal plane of symmetry. So the things I gave you was PF5, NF3, BClF2, H2O, and CH4. These are the molecules that I gave you, and I asked you to find out which molecules, if any, have a sigma H. Here again, 35% of the students got it wrong. So that's the reason why I thought I had to bring this up to the class. We defined sigma H as a plane that is perpendicular to the highest fold rotational axis of symmetry, right? That's the definition of a sigma H. So before you answer, you need to know the Lewis structures of these molecules. And of all these molecules, only PF5, because we have phosphorus in the middle. This is a trigonal bipyramidal geometry. So these are the 5 fluorines. The highest fold rotational axis of symmetry for this molecule is C3. That is your FPF along the axial lines. And there is a plane that is the P and the 3 equatorial fluorines. That plane is your reflection plane because that reflects the F to F here. So that's your sigma H. So that's the only correct answer here. All the other molecules, if you look at NF3, it is a trigonal pyramidal molecule. It has no sigma H. Some of you, 2 or 3 of you have picked up this being the answer, BClF2. You know, one can argue that this may have sigma H2 because the highest fold rotational axis of symmetry here, sometimes people may think this is C1 and then say, well, there's a molecular plane, all right? But the only problem with those thing is, if you write the BClF2 structure, so your boron is here, your chlorine and the 2 fluorines. That's a planar molecule, trigonal planar, and the highest fold rotational axis of symmetry for this molecule is going to be a C2 along the BCl line. Now, if you try to look at a plane perpendicular to this, you don't have a mirror plane. But if you picked up C1 as your rotational axis of symmetry, yes, then it has a sigma H. So there is some ambiguity. So for those people who mark this as the correct answer, I manually adjusted the grades. So just in case you are wondering why your final grade is different than the one that you got immediately after the exam, is because I went over each one of these questions carefully and tried to see if there is a possibility of ambiguity there. Okay. While there is, if you strictly look at this, there is no ambiguity, but for some people, it may look slightly different. So that is the answer. Similarly, I gave you a bunch of molecules and I asked you to find out which of these molecules belong to CS point group? So CS, we said, a molecule that has no other symmetry elements except for a plane of reflection. So of the molecules that I've given you, the NH2Cl, the trigonal pyramidal molecule, has no axis of rotation, no points of inversion. The only thing it has is a plane, reflection plane, that contains the NCl bond and bisects the NH bonds. So that plane that contains NCl is the reflection plane. So that is the only molecule that has a CS point group. That question, I think 32% of them got wrong. Moving on, I asked you another question. Which of the following complexes cannot exhibit cis-trans isomerism? So one was PTCl3Br. Okay. And then there was another example of CH3Br. So the other one was PTNH3 twice Cl2Br2. That was another complex that I gave you. And then there was another one, PTNH3 twice Cl2. So the question was, which of them do not exhibit cis-trans isomerism? Right. So the choice is very clear here. You cannot have a cis-trans isomerism if you have an odd distribution of the ligands. So you have 3 to 1 here. So if you look at PT Cl3Br, there is only one way of writing it, 1 Br in one corner and 3 here. So there is no cis-trans isomerism in this. However, if you were to replace 2 of these ligands by NH3, then you will have, so this one, for example, PTNH3 twice Cl2 will have cis-trans isomerism because you have 2 ways of arranging the ligands. Okay. So if you have odd number of ligands, like 3 is an odd number, 1 is an odd number, then there is a possibility that you will not have cis-trans isomerism. Similarly, if you look at the octahedral complex, the amino-bromo-chloro complex of platinum, we have a possibility of arranging this in a cis or a trans fashion. We talked about them in the class. So these two can exhibit, but this and methyl bromide, which is a tetrahedral complex, tetrahedral complexes cannot exhibit cis-trans isomerism because all sides are equal. That was what was being tested there. So hopefully you will not make that mistake moving forward. Similarly, in one, I asked you for the oxidation state of platinum and gave you a complex PTNH3 3 times Cl. So the whole complex will have a -1 charge. Since chloride is -1, platinum should be +2. So that should be the answer. It's a very simple one. But some people, for 15% of the people, got it wrong. So please make sure that they don't make those mistakes. And the next question, I did ask you, I gave you a list of ligands, the formula and the name as it should appear in the name of the complex. For example, if you have Cl minus, it should be chloro, not chloride. I asked you to go over the table and find out which one of them did not match the one. So the one that I gave you was Cn minus, and I call that cyanide. That is the one that does not match. Cyanide in complexes is written as cyano, not cyanide. The ide goes into O. So chloride goes chloro, fluoride goes fluoro, sulfide goes sulfur, and Cn minus cyanide goes into cyano. So there was also another one question. If you have OH minus, it is called hydroxyl. Some people got a little bit confused. Maybe this is not matching name because we did not cover too many hydroxide complexes. The name of the OH minus is hydroxide. So when you have an ide, it should turn to O. So hydroxyl is the name of the hydroxide in a coordination complex. So this is not the correct choice. The correct choice is cyanide to go to cyano. All right. So that is how the names change. The next question, which disturbed me quite a lot because I had only 40% success in the class, I asked if you take this complex NH4 AgCN2 complex, if I dissolve it in water, what type of species will be there? In other words, I'm asking you, how does this complex ionize in water? So just like any salt, the complexes break down as cations and anions. So the correct answer should be NH4 plus and AgCN2 minus. So these are the species that you get. But some people answered this question as NH4 and Ag plus and Cn minus. They are completely breaking apart. And some people wrote, depending on the choice, you know, like NH4, AgCN and Cn minus. And sometimes we put a plus here and a minus there, NH4 minus. Those are not the correct choices. The correct answer is look at the complex, find out the cation and the anion. And when you dissolve the complex in water, that is how they break down. Just like sodium chloride breaks down to sodium plus and Cl minus. Well, sodium chloride is a simple salt, but here we're talking about a complex ion, but the rules are still the same, anions and cations, right? So that was a little bit of a disappointment for me. The next question that was also a little bit disappointing was the point group for hydrotelluric acid. Hydrotelluric acid has a structure like this with a bond angle of 90 degrees. I said that already. In the question, we said hydrotelluric acid has a HTH bond of 90 degrees. If that is the case, what should be the point group of this molecule? Okay. So first thing is you need to find out the highest full rotational axis of symmetry, which if you look at this, that's your C2, right? And there are two planes of symmetry, one that contains the C2 like this, the other one is a plane of the molecule itself. So there are two sigma V's and a C2, so this should belong to C2V. There are a good number of students did not get that right. So I just want to make sure that this is how you answer the question. All right. Moving on. This is another one. I kind of named the complex and I asked you to write the formula, that is chloroamine bis ethylene diamine chromium 3 sulfate. That was the question. And the answer for that will be Cr NH3 Cl ethylene diamine En twice, and because it is a both amine and ethylene diamine are neutral ligands, so chromium is 3 plus, this complex should have 2 plus charge on top of it, so that should be just one sulfate. Some people picked up a choice with sulfate in the coordination complex. That's not correct, because by the name, we know that the coordination complex is a cationic complex, and the counter anion here happens to be sulfate, so that should be named separately. So that was one small thing. In the next one, I gave you a bunch of molecules and I asked you which of the molecules might have an inversion center. So CH3Cl, does it have inversion center, folks? There's no way it can have, right? There is no, it's a tetrahedral molecule, none. The other example I gave you was CO2, which we know is this. Of course, that carbon is your inversion center right there. So this is yes. And the next example I gave you, I think was TTCl3Br complex. That cannot have inversion center because you have platinum here, it's a square planar complex, Cl, Cl, ClBr. So there is no inversion center here. You can have an inversion center if this bromine were to be chlorine. If all the ligands are chlorides, then you will have an inversion center, otherwise no. Okay. So that was something 20% of the people approximately got wrong. The other example I gave you was C2H2Cl2Br2. Again, depending on how you write the formula or how you arrange the atoms, it may or may not have, but there is a possibility that if you arrange them right, you can have inversion center. The arrangement of CCHClBr, similarly HBr, H and Cl, if you write it that way, then there is a possibility of getting an inversion center. So the correct answer to that question is both CO2 and C2H2 Cl2Br2 have the potential to have the inversion centers. That's the correct answer. Approximately 31% of them did not get that right. All right. So the next question, I think, was done very well by everybody. That was, I gave you which of the ligands will most likely combine with a soft ion such as mercury 2+. Mercury 2+ is large, smaller charge, so highly polarizable, so extremely soft. So then I gave you choice like N3-, C3-, O2-, F-. I gave you these ligands and I asked you which one is most likely to bond with the mercury 2+. So clearly these two are extremely small, so they are very hard. Of all the choices, you have the sulfide. That is the most soft one. So you would expect sulfide to bond with Hg2+. So the correct answer is the sulfide ligand. All right. I mean, in day-to-day life examples too, I mean, this is the chemistry that we learn, but if you have a mercury spill in the lab, the thing that you do is immediately spray some sulfur on top of it to get it cleaned up. Even today, if you have a spill of mercury on the desk or on the floor, the mercury cleanup kit will have a powder, a yellow-looking powder, which is nothing but sulfur, because sulfur binds with mercury very strongly, thereby allowing you to remove it. As you know, mercury is like a liquid, but when you put the sulfur on top of it, it forms HgS, which is a solid that can be easily cleaned up. All right. So that's the chemistry that we're talking about here. The rest of the 5 questions were about the molecular orbitals. Again, some of you have had some questions on this. So for example, I asked you, given a set of orbitals like px and s, px and py, s and s, s and pz, which of the combinations might give you a sigma-like orbitals, bonding orbitals, sigma, not pi. Right? So if you look at px and py, there's no way you can have a sigma bonding. You can't even have a pi bonding too. So there's absolutely no way they can interfere. And px and s, there's no way, because remember I told you in the question that the bonding axis is the z-axis. So if you have two different atoms joining along the z-axis, so the s of one atom and px of the other atom is not going to make a sigma orbital. So the only combination that is possible is an s and a s, or s and pz, that is possible, or a pz and pz, that is a possible sigmas. So these three can give sigma combination, while others don't. This is purely articulated based on the orientation of the orbitals to have an effective overlap. So that was one question, I think.
Professor, for the pi bond instead, you would have an overlap with the px and py, right?
Hmm? No, px and px, py and py.
Yeah, sorry, px and py, yes.
So that is the pi interaction, yes. You need to have proper orientation. Right? We talked about this in the class. Does that make sense, Bhavesh?
Yes.
Excellent, very good. And then I gave another question. The nitrogen has 10 valence electrons. When you arrange 10 valence electrons in the molecular orbitals, using the scheme that we talked about, what will be the bond order for the nitrogen, right? So we talked about this, 1 sigma 2, 2 sigma star 2, and 2 pi 4, and 3 sigma 2. So if you look at that contribution, we have 2 plus 4, 6 plus 2, 8 of them in bonding, only 2 in antibonding, divided by 2, 1/2 of the difference in the number of electrons from bonding and antibonding orbitals, that comes to 3. So that should be the bond order for the nitrogen. Most of you got this wrong. I'm sorry, most of you got it right. So I was very happy with that. The next question I had was a conceptual question. How do you make a bonding orbital? Is it a constructive interference of atomic orbitals, or a destructive interference of atomic orbitals, or bonding, no bonding? So many choices. Basically, we talked very extensively that the bonding orbitals are always made by the constructive interference of the individual atomic orbitals. So that is the correct answer for that. And finally, I gave you a question about a diboron molecule, B2, and asked you how many unpaired electrons this B2 will have in its molecular orbital picture. Again, if you look at the valence electrons, boron is 1s2, 2s2, 2p1. So there are 3 electrons on each boron. So you have 6 valence electrons. So similar to the nitrogen scheme, we go with 1 sigma 2, 2 sigma star 2, and 1 pi 2. As you know, the pi is a doubly degenerate level, which implies that there are 2 levels. So you have 2 electrons in both of them in the pi. So for that reason, the diboron molecule has 2 unpaired electrons. In other words, it is magnetic, compared to nitrogen that does not have any unpaired electrons. Does that make sense, folks? It kind of gives you a summary of the exam. You see how simple it is, but still some people were not paying attention, because in this inorganic chemistry, the devil is in the details. Again, I tried not to introduce new molecules for you, because I tried to choose the examples that we have worked out in the class so as to make your life easy. And you had the entire resources available at you, right? You had the textbook, you have the lecture notes, and you had ample time to do the exam. Okay, any questions on this exam so far? Anything that is not clear? Is that okay? As you can see, the entire exam, there is nothing that we have not covered in the class. And it kind of had good questions from molecular orbitals, point group symmetries, and also coordination complexes. So the final exam will have all the topics from the exam 1 about the atomic structure and the molecular structures to the exam 2, and it will also have some additional questions from what I just sent you, acid-base chemistry, that we will talk about next week, and medicinal inorganic chemistry, and finally the descriptive chemistry of hydrogen. Okay.
Professor, this question is a little bit in advance, but do you have a rough number of how many questions will be from the old material and how many will be from like the new section?
I have not written the exam, so I can't tell you now. But usually it's about anywhere between 60-40 to 75-25. So if you're good up to this point, then the chances of you failing the final is very remote. You will pass. I know that I didn't answer your question properly, but I just gave you a wide range there.
Thank you, Doctor.
Any other questions, folks? So next week, we'll be starting with acid bases. So please read the chapter and the book chapter acid bases. And I also gave you a PowerPoint to go over that kind of summarizes the concepts that we'll be talking. So it'll be a lot easier if you were to read the book before. We can discuss that next week, next Wednesday. If possible, I'll try to put a voiceover PowerPoint for the acid-base chemistry so we can discuss Wednesday. All right. Okay, if there are no further questions, I know that some of you have Thanksgiving plans. You've given me emails that you plan to leave or spend time with the family, but whatever you do, one request is please stay safe. Okay? It's not funny. If we can be patient for another 3-4 months, there are 3 very good vaccines that have showed enormous promise, but we have to be alive to use those vaccines. So let's call this an investment year. We will reap the benefits next year. So for next 3 months, not only your own safety, but safety of your parents or grandparents or any friends with any pre-existing conditions. So please stay away from them. You know, we have survived, you know, almost, what would I say, 9 months. Another 3 months, we'll be fine. We'll be done with the virus. It will be behind us. Next year, by this time, we would not even worry about virus. That will be history. That will be in our rearview mirror. But until then, please, for you know, for your own sake, for your own family's sake, stay safe and stay sober. All right. So I wish you all a very happy Thanksgiving and see you next week with a new topic. All right. Thank you all.
Thanksgiving, Professor.
Happy Thanksgiving. Have a good one.
Thank you. Thank you very much. Thanks for everything.
Mhm.
Thanks, folks. Thank you.